Welcome to Dark Sky Dive, where we explore the engineering marvels that allow humanity to peer into the deepest cosmic abyss. On this planet, there are specific places where humans choose to build machines that look deepest into the silent universe. These locations are not found in bustling cities, nor are they situated in the comfortable flatlands where most people live. They are located on the summits of desolate mountains, where the air is thin, winds howl, and temperatures drop rapidly. This is exactly where the giant ground-based telescopes are born, rising from the rock to challenge the limits of vision. These machines possess the ability to see through billions of light years, observing early galaxies and seeking Earth-like planets. They are hunting for the faint signals of life and the origins of matter in the vast darkness of space. But before they can ever see the universe, these machines must survive a construction journey that is incredibly harsh and demanding. Why must we place these delicate scientific instruments on the most dangerous and inaccessible mountain peaks on our entire planet? The light from distant stars is extremely weak when it reaches Earth, and it is easily destroyed by our atmosphere. Just a little turbulence from air, water vapor, dust, or artificial light is enough to ruin valuable scientific data forever. Therefore, scientists are forced to take telescopes to the highest and driest places found anywhere on the planet's surface. Consider the Atacama Desert in Chile, a place so dry that some parts have not seen rain for decades. Or the summit of Mauna Kea in Hawaii, standing tall above the clouds, protecting the view from lower atmospheric moisture. Here the sky is so dark that the Milky Way casts a shadow, and the air is incredibly stable. However, this perfection implies a difficult truth. Every single piece of material must be transported to these lifeless zones. Every bolt, every steel beam, and every fragile mirror must be hauled up roads where almost no life exists. The heart of a telescope is not the computer or the software, but the primary mirror that captures the light. Unlike small telescopes that use a single glass pane, modern giants use dozens or even hundreds of segments combined together. Each segment is several dozen centimeters thick and weighs between 1 and 2 tons. Yet it must be perfectly shaped. They are polished to a precision where the error margin is smaller than 1,000th of a human hair strand. The polishing process takes years. A single vibration or uncontrolled temperature change could ruin the entire glass segment forever. Once finished, each piece is coated with a reflective layer of aluminum or silver, only a few nanometers thick. This coating is essential for reflection, but it makes the surface incredibly delicate and sensitive to the environment. The mirror segment weighs tons, yet it is more fragile than the household glass you use in your kitchen. Transporting them up the mountain is like moving a crystal egg up a rocky path filled with deadly potholes. The transport vehicle must travel slower than a walking pace, utilizing a special damping system to prevent any vibration. They must avoid shaking at the maximum level. A trip of just a few dozen kilometers can take several days. If a single mirror segment breaks during transport, there is no backup plan available, only years of restarting the process. The cost of failure is not just money, but time. Time that scientists cannot afford to lose in their research. A giant telescope is not only massive in size, but it must also be mechanically precise to the absolute extreme. The entire metal structure stands as high as a multi-story building and weighs thousands of tons of heavy steel. Yet it must rotate smoothly to track the movement of the Earth without any friction or mechanical stuttering. Just a small deviation during installation is enough to cause the light to miss the focal point completely. Engineers use laser sensors and automatic alignment systems to ensure every component is exactly where it needs to be. They simulate the movement of the sky in real time, adjusting for the rotation of the planet every second. The goal is to keep the mirror segments in position, even as temperature, wind, and gravity constantly change. Even on the mountain peak, the atmosphere still causes interference, blurring the images of distant stars and galaxies. The solution is adaptive optics, one of the most complex technologies ever invented by human ingenuity for astronomy. This system projects a powerful laser beam into the sky, creating an artificial star in the upper atmosphere. Computers analyze how the atmosphere distorts the light from this artificial star to calculate the necessary corrections. Then, the secondary mirror of the telescope deforms thousands of times per second to compensate for that turbulence. The result is an image so sharp that it rivals or even exceeds space telescopes in certain wavelengths. Before the telescope can truly see the universe, it must undergo thousands of hours of silent testing and calibration. There are endless nights where the telescope simply rotates without observing anything, just to learn how to balance itself. Some errors only appear after months of operation, and each one can delay the project progress by years. Then comes the moment of first light, when the giant machine finally opens its eye to the real universe. There are no fireworks, no loud applause initially, just scientists silently staring at their screens in anticipation. Tiny points of light appear, representing photons that left their home galaxy billions of years ago to reach us. Each photo is not just data. It is the result of decades of labor, billions of dollars, and extreme precision. Why do humans continue to build telescopes that are larger, more expensive, and more complex with every generation? Because every new generation of telescopes allows us to look further, deeper, and answer questions previously unreachable. We build these giant machines not to show off technical power, but to answer the oldest human question: where do we come from? And in this vast, silent cosmos, are we truly alone or accompanied? These cathedrals of science stand on the mountain peaks, silently watching, waiting for the universe to whisper back. The engineering required to build them pushes the boundaries of what is physically possible for human construction. Even after construction, the maintenance of these giants is a never-ending battle against the elements of nature. They must endure freezing temperatures and ice storms while keeping their internal organs warm and fully functional. Temperature control is vital. If the mirror is warmer than the air, it creates turbulence that ruins the image. So, during the day, the massive mirrors are refrigerated to match the expected temperature of the coming night. As the sun sets, the dome opens, and the telescope temperature is perfectly synchronized with the outside air. The control room becomes the brain of the operation, where astronomers dictate where the giant eye should look. Despite its weight, the telescope can slew across the sky with the grace of a ballet dancer. This movement is powered by motors that are strong enough to move a ship, yet precise enough for surgery. When observing planets like Jupiter, the adaptive optics system reveals details that were once impossible to see from Earth. Ground-based telescopes can now capture images that rival those taken by probes sent to the planets themselves. But they don't just take pictures. They use spectrographs to break light down into its chemical fingerprints. This allows scientists to analyze the atmospheres of planets orbiting other stars, looking for signs of water or oxygen. The search for biosignatures is one of the primary missions of these next-generation giant ground-based telescopes. Often, these telescopes work in conjunction with others around the world to create a global network of eyes. The data collected is transmitted instantly via fiber optics to supercomputers located in valleys far below the summit. Processing this data requires immense computing power to filter out noise and reconstruct the true image of the cosmos. Let us remember the protective dome itself, a marvel of engineering designed to shield the telescope from storms. It must be completely watertight and windproof, yet able to open fully in just a few minutes. Special vents control airflow to prevent turbulence inside the dome, which would distort the telescope's sensitive vision. Building these domes at such high altitudes is dangerous work, requiring oxygen masks for the construction crews. At these heights, the oxygen level is only about 60% of what it is at sea level. Mental sharpness declines and physical exertion becomes exhausting, making the precision work even more difficult to achieve. Yet, thousands of engineers and workers dedicate years of their lives to build these monuments to human curiosity. The secondary mirror, suspended high above the primary dish, must be held with absolute rigidity against the wind. It is supported by thin vanes designed to block as little light as possible from reaching the main mirror. The light bounces back down through a hole in the primary mirror to the instruments located underneath. These instruments are often the size of cars, cooled to near absolute zero to detect faint heat signals. Every few years, the mirrors must be removed and recoated, as dust and oxidation degrade their reflective power. Robotic arms or cranes carefully extract the segments one by one, a process that continues throughout the telescope's life. The old coating is stripped away with acid, and the glass is washed until it is chemically pure. Then a fresh layer of aluminum or silver is applied, restoring the mirror to its original perfect condition. It is then reinstalled and realigned with the rest of the array, ready to collect starlight once more. We are currently entering the era of extremely large telescopes, machines that dwarf everything we have built before. The European Extremely Large Telescope, for example, will have a main mirror nearly 40 meters in diameter. The giant Magellan telescope uses 7 of the largest single-piece mirrors ever made, arranged like flower petals. These projects are so expensive and complex that no single country can easily build them on their own. They require international consortiums, bringing together the best minds and resources from nations all around the globe. Builders must also respect the local environment and the cultural significance of these mountains to indigenous populations. Sustainable practices are implemented to ensure these scientific giants do not harm the pristine nature surrounding them. As the Earth rotates, these telescopes work tirelessly, collecting photons that have traveled for billions of years. They allow us to look back in time, seeing the universe as it was when the first stars ignited. They help us map the invisible web of dark matter and understand the dark energy expanding our universe. Closer to home, they track asteroids that could pose a threat to Earth, acting as planetary guardians. They monitor the weather on the planets of our own solar system, watching storms on Neptune and volcanoes on Io. But the most exciting prospect is the potential discovery of biological signatures on a rocky planet elsewhere. If we find oxygen and methane in the atmosphere of a distant world, it would change human history forever. Ground telescopes work in partnership with space telescopes like James Webb, each providing different pieces of the puzzle. While space offers clarity, the ground allows for much larger mirrors, collecting far more light than anything in orbit. Also, instruments on the ground can be upgraded and repaired easily, keeping the technology constantly at the cutting edge. The future of astronomy stands on these mountain peaks, grounded in rock but reaching for the infinite stars. Night after night, the data accumulates, slowly revealing the structure and history of everything that exists around us. These machines are simply extensions of the human eye, magnified millions of times by the power of engineering. They represent our patience and our determination to understand a universe that is vast, ancient, and largely silent. Sometimes, the most important discoveries are the ones we were not looking for, found by accident in the data. There is a profound beauty in the machine itself, a perfect marriage of heavy industry and delicate optics. Built to last for decades, These observatories will serve multiple generations of scientists and curious minds. They inspire young people to become the engineers and astrophysicists of tomorrow, continuing the quest for knowledge. The images they produce are works of art, painted by the laws of physics and captured by human ingenuity. They remind us of our humble place in the cosmos, a small blue rock orbiting an average yellow star. Yet they also demonstrate the greatness of the human mind, capable of understanding things far beyond our physical reach. There are still limits to break. Engineers are constantly designing better sensors and faster correction systems for the future. Artificial intelligence is now joining the team, helping to analyze the flood of data these giants produce every night. It is a partnership between human creativity, heavy machinery, and advanced software, working in perfect harmony. As dawn breaks, the dome closes. The telescope sleeps, but the data it gathered travels around the world. While the machine rests, the human work begins, interpreting the whispers of light collected from the dark sky. These giant telescopes are the windows through which we view our origins and, perhaps, our ultimate destiny. They are built on the firm belief that understanding the universe is essential to understanding ourselves as a species. From the desolate mountain peaks, we continue to watch, to listen, and to learn from the silent stars. The construction of these giants is a testament to what we can achieve when we aim for the impossible. The journey of discovery never truly ends. It only expands with every larger mirror we manage to build. Thank you for joining us on this journey to the high frontiers of astronomy and engineering excellence. Remember to look up. This is Dark Sky Dive. We will see you in the next documentary.